In the last lecture, we discussed Holder's inequality. Now in this lecture, we will discuss an application of Holder's inequality, that is Minkowski inequality. Minkowski's inequality. So we'll discuss this statement. Minkowski's inequality. Let X and mu be a major space. And 1 is less than p less than infinity. Take two elements fg in LP mu. Then what do you have? Then this sum f plus g also belongs to LP mu. And LP norm of f plus g is less than equal to LP norm of f plus LP norm of g. We put this as inequality number 1. So proof. Since we know by triangle inequality, since m mod of f plus g is less than equal to mod f plus mod g, so we have LP norm of f plus g. This by definition you know, this is equal to t equal to x mod f plus g p d mu power 1 by p. And now we use this inequality. This is less than equal to dx mod f plus mod g power p d mu 1 by p. Put this as equation number 2. So what do you prove? This inequality is less than equal to norm of fp plus norm of gp. Means LP norm of this inequality is less than LP norm of f plus LP norm of g. This we have to prove. Now, so let's discuss. Now, integral over x mod f plus mod g power p d mu. This you can write as, take this one mod f plus mod g power 1, and rest you have mod f plus mod g power p minus 1. This you have d mu. Okay, so this will, you can write mod f plus mod g p d mu plus integral x mod g mod f plus mod g or p d mu. Okay, so we'll apply now Holder's inequality this term and this term. So by Holder's inequality, this you can write this value will be equal to, this value you can write equal to yes. Now by Holder's inequality, we have integral x mod f plus mod g power p d mu, and this is less than equal to, so we'll apply Holder's inequality to this term and this term. So what you get here? Integral x mod f power p d mu power 1 by p integral x, second term here, mod f plus mod g. Already you have p minus 1 power q, 1 by q. This you have. Okay, so for second term plus integral x mod g power p d mu power 1 by p, and rest you have integral x mod f plus mod g power p minus 1 into q power 1 by q. This you have. This value is equal to norm of f, LP norm of f, and this value equal to LP norm of g. You can take this term as common, so you get LP norm of g. This value equal to integral over x mod f plus mod g power p d mu power 1 by p, because p minus 1 into q will be equal to p. You can calculate easily this value, because p minus 1 into q will be equal to p. You can calculate from 1 by p plus 1 by p plus 1 by q is equal to 1. You know, p and q are conjugate exponents. Put this as equation number 3. Okay. You know, since y equal to xp, p get, you know, this one is convex for x getting to 0. Okay. You have this convex for x getting 0. You know the value of convex. If phi is set to convex, value phi from a function, I will give the definition, a function phi from R to R is convex if phi of ax alpha x plus beta y is less than alpha phi x plus beta phi y for all x y belongs to R, and with the condition that alpha plus beta such that alpha plus beta is equal to 1. Here alpha plus beta equal to 1. This you know the definition of convex function. Okay, you have done in the real analysis course. Is convex for x getting 0. We have this value mod f power g over 2 power p is less than 1 by 2 mod f p 1 by 2 mod gp. Okay, this put this equation number 4. So what do you get here? So now we have shown that LP norm f plus g is less than equal to this term norm of f plus integral x mod of f plus mod of g power p d mu 1 by p. So now you see this, from this value you can see that if f belongs to LP mu and g belongs to LP mu, okay, then f plus g, then mod f plus g, mod f plus mod g also belongs to LP mu, and this shows that what you have shown, f plus g also belongs to LP mu. Okay, so from here, so this will belongs to, so it means f plus g will belongs to LP mu. Means I mean, if from here question 4 we can conclude that f plus g belongs to LP mu. From 4 it is clear that if f belongs to LP mu and g belongs to LP mu, then F plus G also belongs to LP. Okay, so you have this one. Okay, so now if this integral mod F plus mod G power P, this value is 0, d mu equals 0. Then yes, from equation 2 here we have equation 2, this one, if this value equals 0, so this value is also 0, so there is nothing to be proved. Then in view of equation second, there is nothing to be proved. There is nothing to be proved. So we assume that, assume integral x mod F plus mod G power P is non-zero. Okay, so now we'll use equation number 3, this equation. Okay, from 3 we have integral x mod F plus mod G power of P d mu. This you have. So what you are doing here, okay, so we are dividing through by this one. So what you get here, this power, already you have one power 1 P, and this value you are left with this one only, not LP norm of F plus LP norm of G. So this is less than equal to LP norm of F plus LP norm of G. So this will imply that integral x mod F plus mod G power P d mu, 1 minus 1 by P, 1 by P plus 1 by Q equal 1, and this value will equal to, what you will get? Sorry, what do you get here? Okay, this value is 1 by Q, sorry, this value is 1 by Q. Okay, so what do you get here? Power 1 minus 1 by Q. So you get this equal to 1 by P, because 1 by P plus 1 by Q equal to 1, correct? And this value is less than equal to LP norm of F plus LP norm of G. This you have. Okay, correct. So, and this value, this is nothing but, thus, use the, equation number 2 and equation number this 5. Equation number 2 we have this one. I'll show you from equation 2. This one, what you get here? Thus from equation number 2 and 5 we have LP norm of F plus G is less than equal to LP norm of F plus LP norm of G. Thus, equation 1 holds. Okay. So this proves the Minkowski inequality. So a small result will have was an exercise. You can put it as exercise. Show that LP mu with this LP norm, this norm is a normed linear space. Linear space. Okay. This is a trivial exercise.